In question 43, it says a ball is thrown vertically upward with a speed of 25 meters per second. We want to know A, how high does it rise? B, how long does it take to reach its highest point? C, how long does it take to hit the ground after it reaches its highest point? And D, what is its velocity when it returns to the level from which it started? Let's draw a picture of this so we can see. In this problem, I'm going to draw a very simple sketch of a ball being thrown vertically upwards towards some highest point. The arrow indicates that direction. Now, the only piece of information we're given is that the ball is launched with some speed of 25 meters per second. That's all we know. So from this point, we have to take whatever information we have and identify a concept. Well, now, since the ball is rising through the air, the ball is going to slow down because of gravity. Since the ball is going to slow down, that means the ball is going to negatively accelerate. It's going to be moving in a particular direction, but slowing down as it does so. So this is an example of a constant acceleration problem. But here's the difference. This is a constant acceleration due to gravity. Otherwise known as free fall acceleration. Okay, so just for a point of clarification, free fall acceleration is constant acceleration, but it's constant acceleration with two major things that go along with it, okay? A couple of points that go along with this. Number one, if an object is constantly accelerating because of Earth's gravity, then its acceleration in the vertical direction is equal to negative g, or 9.8 meters per second squared. It's a constant value. And what that means is objects are going to, if they're thrown upwards, slow down at a rate of 9.8 meters per second every second they travel upwards. Or if they're falling, they will speed up at a rate of 9.8 meters per second every second. The other thing that we need to know about the free fall acceleration is that the velocity at the top is equal to 0. That's a very important point because the top could be the end of the problem, like this. The ball is reaching its highest point at the top, therefore the velocity at the top is 0. It has to be 0 because the ball has to be able to stop, turn around, change directions. Well, what if the object started from the highest point? So say, for instance, somebody dropped a ball from a certain point. Well, that means the velocity at the starting point is 0. So the velocity at the highest point is going to be 0. Now, a couple exceptions to that rule would be if, let's say, a ball is being dropped, but rather than being dropped from the highest point, it's being thrown upward or thrown downward, and then proceeds to fall farther downward. Well, that could happen, but the majority of the time, the velocity at the top of a path is going to be 0. So we're going to take that into account as we work on problems like this. All right. The beauty of doing these type of problems is we don't have to change a whole lot. We simply need to substitute a for a negative g, and then substitute 9.8 for that value of g. Okay, and by the way, on the AP exam, it is fully acceptable to substitute the number 10 in place of g. I do this, many other physics teachers do this, and it's accepted on the AP exam, College Board accepts this. So why not go ahead and use 10 simply because it will make your calculations a lot simpler. The only time I ask that you use 9.8 for a G calculation is when you are doing a lab that involves G. Okay, so back to this problem. We have a ball that's being thrown upwards. We determine that the concept is constant acceleration, and as such, we need to list the variables. The variables are, now instead of x and x naught, v, v naught, a, and t, we need to do the following. X now becomes y because we're going in the y direction upwards instead of the x direction horizontally. X naught becomes y naught. V is the velocity at the end of the vertical movement. V naught is still V naught, initial velocity. A becomes a negative g, in which place I'm going to substitute the number 10. So for g, I substitute 10. And the negative I substitute in the equations right here, here, and here. We'll get more into that in a second. And then t is still t. Time doesn't have a direction. So now we take this list one more time. If I want to know how high does it rise, well, here's what I know. I want to know how high it rises. That means y becomes my question mark. I want to know how high it rises. Well, y effectively becomes the height. Y naught is the initial position, which in this case would be at the lowest level. That would be 0. We're starting at the lowest level. V naught at the bottom is 25 meters per second. We don't know the time. And we do know the velocity at the top. The velocity at this highest point is 0. So velocity at the top is equal to 0. So now, looking at this list here, for part A, I need to come up with something that will help me find how high it rises. Well, I can see right away that I can't really use this equation. Now, keep in mind, if I were to use that equation, x equals x naught plus v naught t plus 1/2 a t squared, then x becomes y, x naught becomes y naught, v naught t is still v naught t, and then plus 1/2 a becomes minus 1/2 g t squared. So I'm replacing the plus with a minus and the a with a g. That's really the only transformation you need to make with this formula. But the problem is it doesn't really work for us because we don't have time. This is our main unknown. This is our second unknown. We can't have two unknowns in the equation. The first equation will not work either. The first equation has v equals v naught plus at. Now if I were to translate that into vertical motion, v is still v, v naught is still v naught, plus is translated to a minus gt. Well, I don't have time, but more importantly, this equation does not have a y in it. It doesn't help me find how high I'm going. Now, this equation will be very helpful for figuring out how long it takes to reach the highest point. We'll come back to this one shortly. That leads me to the third equation. The third equation says v squared equals v naught squared minus, plus 2a times the quantity x minus x naught. This is still v, and this is still v naught squared. The plus becomes a minus 2g, x becomes y, x naught becomes y naught. So I'm just doing a fair bit of translating here. Okay. So now, once we get to this point, we have to solve this equation for y. Right? How do we go about doing that? Well, Go from your list right here. We know that v at the top is equal to 0, so I can zero out that. 0 squared is still 0. We know that y naught at the bottom is also 0. Okay, this helps to simplify the equation a little bit into 0 equals v naught squared minus 2gy. Well, to solve it for y, I'm going to go ahead and add 2gy to both sides. And we have 2gy equals v naught squared. In order to get y by itself, we will go ahead and divide 2g both sides. And y at the top is going to be equal to v naught squared over 2 times g, or 25 squared over 2 times 10 we plug in for g. Well, we have 25 squared is 625 divided by 20 is roughly around 31.3 meters high. Now part B wants to know how long it takes to reach its highest point. So we want an equation with time in it. Well, this particular equation works very well because we know that the velocity at the highest point is equal to 0. We know this, and we're looking for this. So essentially this equation works perfectly to figure out how long it takes to reach the highest point. Rewriting the equation, we get 0 equals v naught minus gt. We have to solve for t. We can start by adding gt over to the left. And if we rewrite this, we get gt equals v naught. Divide both sides by g. And time equals 25 over 10, which is 2.5 seconds. Now part C wants to know about how long it takes to hit the ground after it reaches its highest point, and what's the velocity when it returns back to that level of the ground. Well, to do C and D, it would probably be wise for us to construct a new picture that represents a different scenario. So here's what we can do. We can have the ball coming from its highest point, in which case the velocity at the top is 0. And here's some of the things we know about it. If I fill out a new list here, y, y naught, v, v naught, a, and t. I don't know time. I know the acceleration is negative g, which is a value of 10 that I plug into the equation. V naught is 0 because this is the initial part of the problem now. Okay, we can think of part C as a brand new problem, where the highest point is now the beginning of the problem and the lowest point is now the end of the problem. So we can essentially construct a new reference frame. Now I don't know the speed upon impact, and I don't mean after impact. The speed after impact, the ball comes to rest. We want to know the speed right before it hits. Now y naught could be the height from which you started with, which is 31.3. We got that from part A. And y could very well be the position that you end up with, which is 0. The ball is going to end up on the ground level. We need to figure out how long it takes. So looking at this information, I have y and y naught, I have v naught, and I've got a and t. So using this information, I can use the second equation, x equals x naught plus v naught t plus 1/2 a t squared. Translated, that would be y equals y naught plus v naught t minus 1/2 g t squared. Cancel everything you can. Y naught, let's see, y is 0 at the bottom when it hits. V naught is 0, so v naught t, the middle term, is 0. And if we rewrite this, we get 0 equals y naught minus 1/2 gt squared. And we're solving this for time. So here's what I'm thinking we can do. Let's take this whole term and add 1/2 gt squared over to the left-hand side. And if we rewrite this, we get 1/2 gt squared equals y naught. Copy that down again. Now at this point, what I can do is I can start solving for t. Now to solve for t, I need to multiply both sides by 2. That's going to get rid of the fraction. And if I rewrite, I get gt squared equals 2y naught. To get t by itself, I have to get rid of g and squared, so the next step, I'll go ahead and divide out the g. Both sides. Rewriting this, I get t squared equals 2y naught over g. Last step in solving it, I'm going to square root both sides. And t is equal to 2 times 31.3 over 10. And when we put that into our calculator, we get roughly about 2.5 seconds. Now that is an interesting conclusion, because if we look back at part B, it took 2.5 seconds to go up to its highest point. Well, apparently it takes 2.5 seconds to go down from its highest point. So if we neglect something called air resistance along the way, then we can make yet another simple pattern that goes along with free fall acceleration, and that is time is symmetrical. Time up equals time down. Lastly, for part D, we want to know the speed at which it is falling from, with the speed when it returns to the level from which it started. So this equation should help. V equals V naught minus GT, where this is 0. And the velocity is equal to negative 10 times 2.5, or negative 25 meters per second. Now, this is also an interesting solution. The magnitude of this is telling you the speed is 25 meters per second. The negative, on the other hand, is telling you the direction, downward. It has a downward velocity of 25 meters per second right before it hits. Well, if you remember, it was launched with that very same velocity. So we have a couple points of symmetry. Velocity at every vertical level along the way is going to be the same up and down. Time going up is symmetrical to time going down. Now these, of course, are assuming that we neglect air resistance in problems like this, but that is going to be the case the entire time in this course. So that leads to 3 very nice and easy patterns that we can make with free fall acceleration.